Welcome to this coding problem walkthrough. In today's session, we'll be tackling problem number 961, titled N repeated element in size 2 an array. Together, we'll explore the problem statement, analyze possible approaches, and break down the solution step by step. Let's dive in and get started. In this problem, we are working with an array called nums, which contains two n integers. Among these integers, there are exactly n plus 1 unique elements. One of these elements appears repeatedly, exactly n times, while all the other elements are unique and appear only once. Your task is to identify and return the element that is repeated n times. Looking at the input and output format, the input is an integer array nums of size 2n. Each element in the array is an integer, and the single repeated element is guaranteed to appear exactly n times. The output will be an integer x, representing the repeated element in the array. Let's go over some examples to better understand how this works. In the first example, the input array is 1, 2, 3, 3. This array contains 4 elements, which means 2n equals 4, so n equals 2. Among these numbers, the element 3 appears exactly 2 times, while all the other elements are unique. Therefore, the output is 3, as it satisfies the condition of being the element repeated n times. In the second example, the input array is 2, 1, 2, 5, 3, 2. Here, the array length is 6, so 2n equals 6 and n equals 3. The repeated element in this case is 2, which appears exactly 3 times in the array. So, the output is 2. These examples illustrate how to identify the repeated element based on its frequency in the array. Now, in the third example, the input array is 5, 1, 5, 2, 5, 3, 5, 4. This array has 8 elements, meaning 2n equals 8 and n equals 4. Observing the numbers, the repeated element is 5, which appears exactly 4 times, while all other elements occur only once. Thus, the output is 5. Additionally, we have some constraints for the problem. The length of the array will always be even in range from 2 to 10,000. Each element in the array will be between 1 and 10,000. Importantly, there is always exactly one integer that is repeated n times, so you don't need to handle cases with multiple repeated elements. Finally, let's consider some edge cases to ensure the solution works for all valid inputs. First, for the smallest possible input size, such as nums containing just 2 elements like 1, 1, the algorithm should correctly identify and return the repeated number. Next, if the repeated number is at the beginning or end of the array, the solution should still work. For instance, in an unordered array like 3, 1, 4, 3, 5, 6, the repeated number may not be adjacent, so the algorithm must be able to identify it regardless of its position. Lastly, it's critical that the solution handles the maximum input size of 10,000 efficiently, ensuring it performs well under all conditions. These considerations will help ensure your implementation is both correct and optimized. To begin, we consider the brute force approach. This is the most straightforward method where we use 2 nested loops to compare each element with the rest of the array. Since the problem guarantees that one specific element is repeated n times, we can identify it by simply counting the occurrences of every number. The process involves an outer loop that iterates through each element of the array, and for each element, an inner loop checks the rest of the array for matches. Once we find the number that appears n times, we return it. However, the major drawback is its inefficiency. The time complexity here is n squared, as every element is compared with all others, leading to quadratic growth. While the space complexity is 1, since no additional data structures are used, the high time complexity makes this approach impractical for larger arrays. This inefficiency is the key limitation of the brute force strategy. A more efficient method is the hash map approach. This involves using a hash map or dictionary to track the frequency of each number as we iterate through the array. Since the repeated number appears n times, we can stop as soon as one number's count reaches n and return it immediately. The steps are straightforward. First, initialize an empty hash map. Then, for each number in the array, update its count in the hash map. If any count reaches n during this process, we return that number. This approach significantly reduces the time complexity to n, as each number is processed just once, and the space complexity is n, due to the hash map. However, a drawback is the additional memory required for the hash map, which can be a consideration for extremely large inputs. Additionally, there's another efficient option, the set approach. Rather than counting occurrences, it leverages the fact that the repeated number will necessarily appear more than once. Using a set, we can identify this duplicate directly. Let's explore how the set approach works. In this method, we use a set to track the numbers we've seen so far. The steps are simple. Start by initializing an empty set. Then, iterate through the array. For each number, check if it's already in the set. If it is, then we've found our repeated number, and we can return it immediately. Otherwise, add the number to the set and continue. The time complexity of this approach is O(n), as we only process each number once, and the space complexity is also O(n), due to the storage required for the set. While the memory usage is still linear, this approach is simpler and faster than the hash map approach because it avoids the overhead of maintaining frequency counts. This simplicity makes the set approach an appealing option for solving the problem efficiently. The set approach stands out as the optimal strategy for this problem. Since the repeated element is guaranteed to appear at least twice, the set provides an efficient mechanism to detect duplicates. Its linear time complexity of O(n) and linear space complexity of O(n) make it both time and memory efficient. Additionally, the implementation is concise and avoids the need for extra bookkeeping, such as maintaining counts, which is required in the hash map approach. There are also some key insights that make this approach especially suited to the problem. First, the guarantee that only one element is repeated n times simplifies the task. We don't need to count occurrences explicitly, as identifying the duplicate is sufficient. Second, a set allows constant time checks and insertions, which aligns well with the problem's constraints. When comparing alternatives, while the hash map approach is also efficient, the set approach is simpler and faster. On the other hand, brute force remains computationally expensive and unsuitable for larger inputs. Overall, the set approach strikes the perfect balance between simplicity, efficiency, and readability, making it the ideal solution for this problem. In this problem, we are given an array of size 2n, where one specific element is repeated exactly n times. Our goal is to identify this repeated element as efficiently as possible. To start, we can consider a brute force approach. The intuition here is straightforward. By comparing each element with every other element in the array, we can count their occurrences and identify the one that appears exactly n times. For implementation, we first initialize a counter, such as a dictionary, to track the occurrences of each element. Then, we use nested loops and outer loop to iterate through each element and an inner loop to count how many times the current element appears. If any element's count matches n, we return it as the result. While this approach works, it has an O(n) squared time complexity due to the nested loops, which can be inefficient for large input sizes. To improve, we can use a more optimized approach involving hashing. By using a hash map to store the frequency of each element, we can significantly reduce the time complexity to O(n). Let's explore this next. To implement the optimized hashing approach, we start by initializing an empty hash map to store the frequencies of elements. As we traverse the array, we check each element against the hash map. If the element already exists in the map, we increment its count. If it doesn't, we add it to the map with an initial count of 1. After processing the array, the element with a frequency of n can be identified directly from the hash map. This method ensures we only pass through the array once, achieving O(n) time complexity. Another optimization leverages a mathematical insight. Here's the idea: if we compute the sum of all distinct elements in the array and multiply it by n, the result represents the total sum of the array if there were no repeated elements. From this, we subtract the actual sum of the array to isolate the repeated element. To apply this, we calculate the distinct sum using a set to eliminate duplicates, multiply it by n, and then subtract the actual array sum. This mathematical approach is efficient, requiring only O(1) space, but it assumes all elements are integers, which is a key limitation. Overall, these optimizations address the inefficiencies of the brute force approach, with hashing providing a robust, general-purpose solution and the mathematical method offering a space-efficient alternative. To dive deeper into the specifics, let's look at the data structures and edge cases involved. First, hash maps, or dictionaries, are instrumental in the hashing approach. They allow us to track the frequency of elements during traversal, with constant time operations for insertion and lookup. Sets are equally important for the mathematical optimization, as they efficiently eliminate duplicates to compute the distinct sum. Now, let's consider some edge cases. One scenario is an array with only one unique element. Here, the logic must handle cases where all elements are identical. Another case involves arrays with non-continuous or negative numbers, which requires careful handling to ensure the mathematical approach works correctly. Lastly, for empty or very small arrays, input validation is crucial to avoid runtime errors. From a complexity perspective, the brute force approach has n squared time complexity and O(1) space complexity, which makes it impractical for larger datasets. The hashing approach is far more efficient, with n time complexity and n space complexity for the hash map. The mathematical method stands out with n time and O(1) space, but it's important to verify that the input satisfies its assumptions. These considerations help ensure that the algorithm is robust, efficient, and adaptable to different input scenarios. Now let's look at the implementation of these approaches in Python. For the hashing approach, we can use the counter class from the collections module. First, we calculate the frequency of each element in the array using counter. Then, we iterate through the resulting dictionary to find the key with a value equal to n and return it. This ensures an efficient solution with clear logic. For the mathematical approach, we start by computing the sum of all distinct elements in the array using the set function. Next, we calculate the total sum of the array and use the formula total_sum distinct_sum / n1 to determine the repeated element. This formula works because the repeated element contributes extra occurrences to the total sum. Both implementations are concise and directly reflect the algorithms we discussed. By understanding and applying these solutions, you can confidently solve this problem with efficiency and clarity. The task is to find the element that appears exactly n times in a 2n-sized array. This solution uses a single loop and is set to efficiently determine the repeated element. First, we initialize an empty set called scene to keep track of unique elements encountered so far. Then, we iterate through each element in the nums array. For each number, we check whether it is already present in the scene set. If it is, this means the element has been encountered before and is the repeated element, so we immediately return it. If the element is not in the set, we add it to the set and continue the loop. This approach works efficiently because only one element is guaranteed to be repeated, and the repetition happens enough times to ensure we encounter it during the loop. The time complexity is n, where n is the length of the input array, and the space complexity is n in the worst case, where all elements except the repeated one are unique. This is the Java implementation for LeetCode problem number 961, n repeated element in size 2 an array. The logic mirrors the Python solution, utilizing a hash set to track scene elements. The method repeated n times iterates through the array, checking if an element is already in the set. If so, it immediately returns that element as the repeated number. Key differences include explicit type declarations in Java, use of the hashSet class for managing unique elements, and the class structure required by Java. The code is efficient, with a time complexity of n, where n is the length of the input array. Here, we are solving the problem with the input array 1, 2, 3, 3. The goal is to find the element that is repeated exactly twice. We start with an empty set called scene. As we iterate through the array, the first number we encounter is 1. Since 1 is not in the set, we add it to scene. The set now contains 1. Next, we look at the number 2. Again, it's not in the set, so we add 2 to scene, which now becomes 1, 2. Then we encounter 3, which is also not in the set, so we add it, making scene equal to 1, 2, 3. Finally, we encounter another 3. This time, 3 is already in the set, which means it's the repeated element. Therefore, we return 3 as the result. In this example, the input array is 5, 1, 5, 2, 5, 3, 5, 4. Once again, we aim to find the repeated element. Starting with an empty set scene, we first encounter the number 5. Since it's not in the set, we add it, and scene becomes 5. The next number is 1, which is also not in the set, so we add it, making scene equal to 1, 5. When we encounter the next 5, we find that it's already in the set. This immediately identifies 5 as the repeated element, so we return 5 as the result. For this example, we are working with the input array 9, 7, 9, 10, 11, 12. As usual, we start with an empty set called scene. The first element, 9, is not in the set, so we add it, and scene becomes 9. The next element is 7, which is also not in the set, so we add it, resulting in 9, 7. When we encounter the next 9, we see that it's already in the set. This tells us that 9 is the repeated element in this array. We return 9 as the result. The algorithm effectively solves the problem by leveraging the guarantee that exactly one element is repeated n times in the array. By using a set, we can efficiently track whether an element has been encountered before. As soon as we find a repeated element, we return it, since it must be the n repeated element. The key insight here is the efficiency of the set data structure, which allows for constant time membership checks. This ensures that our solution runs in linear time, O(n), where n is the length of the array. Additionally, the space complexity is proportional to the number of unique elements encountered before finding the repeated element, which is much smaller than the input size for large arrays. This makes the algorithm both time and space efficient, adhering to the problem's constraints. Here, we analyze the time complexity of the solution. The algorithm makes a single pass through the input array nums, which contains 2n elements. This means the for loop that iterates over the array contributes a time complexity of O(2n), which simplifies to O(n). Now, within this loop, there are two key operations. First, we check if the current number exists in the hash set scene using the number in scene operation. In a hash set, membership checks are highly efficient, taking 1 time on average. Second, if the number is not in the set, we add it using the scene.add number operation, which also has an average time complexity of 1. Both of these operations are constant time, so overall, processing each element in the array involves 1 work. Since this is done for all 2n elements, the total time complexity remains O(n). Now, putting this together, for each element in the array, we perform a constant time operation, either a membership check or an insertion. With 2n elements in the array, the total time complexity is O(n). In the best case scenario, the repeated element is found early, such as at the second position. Here, the loop exits early, and the time complexity reduces to 1. On the other hand, in the worst case scenario, the repeated element is near the end of the array, requiring the loop to process all 2n elements, resulting in O(n) time complexity. Moving to space complexity, the algorithm uses an auxiliary hash set called scene to store unique elements encountered during the iteration. In the worst case, the set can grow to hold up to n+1 elements, since the array consists of n unique elements plus 1 repeated element. Since each element in the set occupies O(1) space, the total space used by the set is O(n). It's important to note that the input array nums itself is not counted as auxiliary space since it is a part of the input and does not require additional memory allocation. Thus, the total auxiliary space complexity of the solution is O(n). Let's compare this with a naive approach. A brute force method would involve comparing every pair of elements in the array to find the repeated one. This would require nested loops, leading to a time complexity of O(n squared). However, the naive approach does not use any extra data structures, so its space complexity is O(1). In contrast, the optimized hash set solution significantly improves the time complexity to O(n) by leveraging the efficient constant time operations of a hash set. The trade-off is an auxiliary space complexity of O(n). Finally, mathematically, the big O analysis confirms these results. The operations inside the loop, like membership checks and insertions, are O(1). When applied to all 2n elements, the total time complexity becomes O(2n), which simplifies to O(n). For space, the hash set stores up to n+1 elements, resulting in a linear space complexity of O(n). Therefore, the final complexities are O(n) for time and O(n) for space, making this a highly efficient solution for the problem. When solving this problem, there are several common mistakes to watch out for. First, ignoring edge cases can lead to runtime errors or incorrect results. For instance, consider scenarios like an empty array, an array with only one element, or all elements being identical. Even though constraints are often provided, failing to handle these edge cases can cause your solution to break. Another mistake is using inefficient approaches for large inputs. A brute force algorithm with n squared complexity might work for small arrays, but for larger sizes, such as n greater than 10,000, this can result in time limit exceeded errors. Remember, efficiency is highly valued in both competitive programming and technical interviews. Additionally, assuming that elements in the array are distinct without validating the problem constraints can lead to logical errors. For example, overlooking multiple occurrences of the repeated element might disrupt your frequency-based logic. Finally, improper use of hash maps is another frequent pitfall. Mismanaging keys, overwriting values, or assuming certain values exist can introduce runtime errors, and while hash map operations are typically O1, incorrect usage can escalate complexity or crash your code. Off-by-one errors and indices are another subtle but common source of bugs. These occur often in pointer-based solutions or binary search implementations, where a slight miscalculation can lead to incorrect results. These issues can be tricky to debug without thorough testing. From an interview perspective, it's crucial to demonstrate awareness of time complexity. For instance, while a hash map approach with n time complexity is efficient, sorting the array, which takes n log n, might not be ideal for larger datasets unless explicitly allowed. Space complexity is another important consideration. When the problem constraints require extra space, you may need to get creative, such as modifying the input array in place or leveraging mathematical techniques. Recognizing patterns across similar problems can also help you generalize solutions. For example, strategies like frequency counting, XOR operations, or Floyd's tortoise and hare method often appear in problems involving repeated elements. And don't forget the importance of clear communication in interviews. Explaining why you've chosen a specific data structure or algorithm, like preferring a hash map for counting frequencies over sorting, demonstrates a thoughtful and structured approach. Now, let's look at some related problems that share similar concepts. For instance, LeetCode 287, find the duplicate number, or LeetCode 169, majority element, involve identifying repeated or dominant elements in arrays. LeetCode 442, find all duplicates in an array, and LeetCode 41, first missing positive, also require careful handling of arrays and constraints. Exploring these problems can deepen your understanding of common patterns and techniques. When it comes to alternative approaches, the hash map method is a reliable choice. By counting the frequency of each element, you can identify the repeated number efficiently with n time complexity. However, the trade-off is the additional n space required for the hash map. Another option is the sorting approach. By sorting the array and checking adjacent elements for duplicates, you can achieve the result in n log n time. This method is slower but uses only one extra space, making it a viable alternative when memory constraints are strict. Finally, the mathematical approach offers another interesting solution. Techniques like using the sum of the first n natural numbers or XOR operations can help identify the repeated element. These methods are efficient, with n time complexity and one space. However, they come with their own challenges. For example, arithmetic-based methods can run into numerical overflow issues, especially with large input sizes, and XOR operations may be harder to explain or debug logically. While these approaches can be elegant, it's important to weigh their advantages and disadvantages carefully. Understanding these trade-offs and when to apply each method will make you better prepared to handle similar problems in interviews or competitive programming. Thanks for sticking through the session. We've summarized the key points of today's problem and discussed the importance of optimization and edge case handling. Don't forget to practice similar problems to solidify your understanding. If you found this helpful, please like and subscribe for more content. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!